Hi folks, and welcome back to educator.com. In this mini lesson we're going to go over page 1 of the worksheet on ramps and inclines. You can find the link to that down below, and I recommend you take a minute, print it out, see if you can answer it, and then come back and we'll check our answers. So take a second and we'll go on to problem 1 here. Number 1, the diagram at right represents a block at rest on an incline. Which diagram below best represents the forces acting on the block? Well, right away I know I'm going to have the block's weight down. We're going to have the normal force, which is always perpendicular to the surface, that direction, and if the block wants to slide down the ramp, then I would expect to see force of friction acting up the ramp. So of these choices, the one that matches on our free body diagrams here is number 4. Weight down, normal force perpendicular to the ramp, and friction acting to oppose the motion of the object up the ramp. Number 2 here. The diagram below shows a 50 kilogram crate on a frictionless plane at angle theta to the horizontal. The crate is pushed at constant speed up the incline from point A to point B by force F. If angle theta were increased, what would be the effect on the magnitude of force F and the total work done on the crate as it is moved from A to B? Now this is a very interesting question because it's somewhat vague about how this would happen. For example, if you're going from A to B, you're going to do the same amount of work assuming that B is at the same height because it's a frictionless plane. Your difference in energy says that you must have some potential energy here, and that change in potential energy depends only on the height, not the route that you take to get there, assuming that it's frictionless. Of course, as the angle theta increases, you're going to see that you're going to have to push harder. You're going to have to apply more force to get it up the ramp. But what it doesn't make clear is, as angle theta increases, are you actually going to a higher B? If that's the case, then you would have to do more work. If instead it's just saying that you have a shorter ramp, another way of getting to the same height, change the angle, but B is it still at the same height, a different angle there, then you'd be doing the same work, but regardless the force is going up. So there are a couple answers here depending on how you looked at the question that could be correct. Instead of worrying about exactly which answer is correct, make sure you understand the basic concept here. As theta goes up, force must increase, of course. And if you considered that B was getting to a higher point, you would have to do more work. If you thought B was at the same point and you just shortened up your ramp, then you would have the same amount of work done. Number 3. In the diagram below, a 10 kilogram block is at rest on a plane inclined at 15 degrees to the horizontal. As the angle of the incline is increased, what will happen to the mass of the block? Well, another trick question there. The mass of the block isn't going to change. The amount of stuff it's made up of is going to remain constant. Number 4. A block weighing 10 newtons is on a ramp inclined at 30 degrees to the horizontal. A 3 Newton force of friction, Ff, acts on the block as it is pulled up the ramp at constant velocity, so acceleration is equal 0, all balanced forces, with force F, which is parallel to the ramp as shown in the diagram. What's the magnitude of force F? Well, let's start with our free body diagram here. We've got weight, we've got F up the ramp, we have force of friction, and our normal force. But notice that these aren't all lined up with an axis. So I'm going to redraw this with my axes this way. And now I have F acting up the ramp. I have the normal force lined up with an axis. I've got the force of friction, and this force of gravity, this weight, I'm going to break into 2 components. A portion that is perpendicular to the ramp, mg perpendicular, and a portion parallel with the ramp, mg parallel, which is equal to mg sine theta. So if we want the magnitude of the force F, we need to realize that if it's moving at constant velocity, all the forces must balance out. So those forces in the x direction must be equal. That tells me that F must be equal to mg sine theta plus the force of friction, where mg sine theta is going to be mg, its weight, so 10 newtons times the sine of 30 degrees plus the force of friction, which is 3 newtons. So 10 sine 30, that's going to be 5 newtons. The force of friction is 3 newtons. Therefore, our applied force must be choice 2, 8 newtons. All right, let's take a look at one more here. The diagram below shows a 1 times 10 to the 5th Newton truck at rest on a hill that makes an angle of 8 degrees with the horizontal. What is the component of the truck's weight parallel to the hill? So we're looking for the component mg parallel to the hill, which is mg times the sine of that angle. Well, if its weight, mg, is 1 times 10 to the 5th, so 10 to the 5th newtons, times the sine of 8 degrees, I can't do that one in my head. We'll use the calculator for that. 10 to the 5th times the sine of 8 degrees is about, I get 13,900 newtons, or about 1.4 times 10 to the 4th newtons. Correct answer there, number 3. All right, that concludes page 1 of the Ramps and Inclines worksheet. If this went great, wonderful, keep moving on. And if it didn't, now would be a great time to go back and review that full lecture from previously here on the educator.com site. Thanks so much for your time and make it a great day.